Here was the short, sweet quiz on spectrophotometry and Beer's Law. Spectrophotometry is another name for that colorimetry. It's that lab procedure of shining different colors of light through a solution and comparing the absorbance of light to the concentration of the solution. So this spectrophotometry or colorimetry is a process that requires colored reactants or products. So here we do have a reaction that starts out dark brown, and as it progresses, it forms colorless products. So it should lighten over time. So spectrophotometry would be an option. Not titration, that's like mixing solutions of known concentration. These are gases. Gravimetric analysis is like separating a precipitate from a solution by filtration. And we know paper chromatography. Paper chromatography is a way of separating components of a mixture of solutions that have different polarities. So this one here, spectrophotometry, is not really about separating the reactants or components of the reactants or products. It's used to determine the concentration of something that might be present, but it's got to be colored, which these are. Here's a really cute set of data. I like this one. They give you this kind of crazy reaction, and again, it's a colored reactant, and it forms colorless products. So I would be able to study the change in concentration of that violet ion over time. The solution should lighten. All right, so they give me all this data as time went by. Looks like about every 30 seconds or so, they measured the absorbance. It says approximately how long did it take for 75% of the initial amount of that violet ion to react. Okay, well, you've got a couple options. One option would just say, okay, well, at time 0, the absorbance was 0.62. So that would have just been the initial solution. The absorbance would have been directly related to the initial concentration. And so you could just say, all right, I'm going to take 75% of that 0.62, and you should get about 0.15. And so I could say, all right, so by the time I'm at an absorbance of 0.15, it took 300 seconds. That would work. Or you could kind of think about half-life. So the first half-life is the time it takes for the initial concentration to go down by half. Or here, the initial absorbance, because absorbance would be directly related to the concentration. So it takes about 150 seconds for the initial absorbance to go down by half. So 150 seconds should be the half-life. So at that point, half of the violet ion has reacted, half of the violet ion remains. Well, then after your second half-life, half of the remaining ion is consumed. And so now we're down to 25% remaining and a total of 75% reacted. 75% is gone. And so that would be the second half-life, which should be after another 150 seconds. So after a total of 300 seconds, that would be 2 half-lives. 75% of the initial violet ion has reacted and 25% remains. So you can kind of go at this one from either angle. You could just look at the percent of the initial amount, or you could go at it from half-lives. This would take 2 half-lives. Here's an absorption spectrum for blue dye. When analyzing the solution, what color of light should be used in the colorimeter, also known as a spectrophotometer? And so we want to just look at the maximum absorbance. So it seems that this blue dye absorbs light best, I don't know, somewhere a little less than 650 nanometers. Which then if I look at the electromagnetic spectrum here, I would choose red light. So I want to choose something that is well absorbed by my colored solution, obviously I'm not going to pick like blue light. Blue light wouldn't be well absorbed by a blue solution. You kind of think about like the color wheel. The opposite colors are absorbed well by a particular solution. Somebody created a graph here. Sometimes these are called standard curves. They're not curvy, they should be straight, where they plotted the concentration of some known solutions and their absorbance. The student used a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers, and they constructed this standard curve graph, which is not a bad graph. They did get a decent linear fit, but the student did observe that there was a little bit of error in one of the points. One of the points at 0.05 molar cobalt did not fall on the graph as it should have. The absorbance was a little bit low. So we're looking maybe for one of these errors that would cause the absorbance to be a little bit lower than what we'd expect. And so it could be that first choice, that maybe inside that little cuvette, maybe somebody decided that they were going to have all good intentions and rinse it out, but they didn't dry it out before adding their testing solution. And so if there was a little bit of water left in the cuvette, that's going to dilute the solution that now I'm intending to test. So the concentration would be a little bit less than I'd expect, and then the absorbance would be a little bit less than what I expect. So I thought it was 0.5 molar or 0.05 molar, but I didn't take into consideration the little bit of excess water that was in the cuvette. The second choice, a few drops of the 0.1 molar cobalt ion standard in the cuvette when the student put in the 0.05 molar standard. So again, maybe they didn't rinse out a previous solution well, but if the previous solution were more concentrated, I would have expected the error to be in that the concentration here would be too high, or I should say the absorbance would be too high. The third, the student used a cuvette with a longer path length than the cuvette used for the other standard solutions. That might come into play later on when I'm ready for my calculations. But here it shouldn't affect the absorbance as long as the concentration is proper. The student did not run a blank between the 0.05 molar solution and the one before it. That's not necessary. A blank would just mean that you use distilled water, and you sometimes kind of have to calibrate the colorimeter to make sure that if I just run water, 100% of the light should shine through the water. But you don't have to do that in between testing solutions. Obviously, I'd want to clean out my cuvette and dry it well, but I wouldn't have to recalibrate in between trials. And finally, I like this one, to determine the moles of iron 3 ions in a 100 milliliter sample of an unknown solution. Excess potassium thiocyanate is added to convert all of the iron plus 3 into a dark red species of this iron thiocyanate ion, as represented by the equation above. The absorbance of the iron thiocyanate at different concentrations is shown in the graph below. So it looks like the absorbance is increasing as I form more of this iron thiocyanate ion. That would be the colored ion. If the absorbance of the mixture is 0.2 at this given wavelength, how many moles of iron plus 3 were present in the 100 milliliter sample? Okay, so the trick here is that they're asking for moles. And so I could find the absorbance on the graph, 0.2. I can follow it over to my graph and down, and I could say that the concentration, technically, the concentration of the FeSCN2 plus is probably about 4 times 10 to the negative fifth. Molarity, 4 moles per liter. Okay, well now if I look at the balanced equation, I am asked about the moles of iron present in the sample. Well, I see that it's a 1-to-1 ratio, so there must also be then 4 times 10 to the negative fifth moles of iron per liter. But the question says that I only used 100 milliliter sample. Oh, brother. So I just set up a little proportion then to say, okay, well, if there would have been 4 times 10 to the negative fifth moles in a liter, how many moles in just 100 milliliters? And that's how we get the 4 times 10 to the negative sixth moles of iron. So I can use the ratio in the balanced equation to go from that red iron thiocyanate back to the original iron plus 3 ion. And then the trick here was to convert that to just moles in a 100 milliliter sample. Now the only other thing that we should just mention is that there is this fantastic equation in your packet. It's in the section of the packet on solutions, gases, liquids, and solutions. This is Beer's law. Beer's law is the equation that lets you kind of quantify the relationship between absorbance and concentration. For the most part, it is a plug and chug kind of equation, where A is absorbance. I'd maybe be given that, or I'm solving for that. Then you've got your molar absorptivity constant, which is a constant. B is the path length. That really is just like the width of the cuvette. Like if this is my little cuvette, this is the path length. Often they're like 1 centimeter cuvettes that we use. And so those two are pretty much constants that you'd probably not solve for. But then C is concentration or molarity. And so most often you'd either be solving for absorbance or solving for the concentration, given one or the other. It's an easy equation that's in the packet. They tell you what all these variables stand for, so it's not something that I would spend 8 days trying to review before the AP exam. I would just know that it's there, and that equation is used in reference to data real similar to this.